Hello there. In this video we're going to give a formal proof of the perpendicular line theorem. So if you do not know what exactly the perpendicular line theorem says, let me briefly state it for you. So we're going to consider two lines. We're going to call it line 1 and line 2. And let's assume they have equations y is equal to m1x plus b1 and y is equal to m2x plus b2. So m1, m2, b1, and b2 are their slopes and vertical intercepts respectively, and they can or cannot be different or the same depending on the particular scenario. And we'll also put in a restriction with m1 and m2 both non-equal to 0. That is, both of these are not horizontal lines. Then if this is true, then line 1 is perpendicular to line 2 if and only if the products of their slopes m1 and m2 is equal to -1. That is, m1 and m2 are negative reciprocals of one another. Negative reciprocals of one another. So we'll give a formal proof, discuss a couple of observations, and in the next video we'll do a couple examples associated with perpendicular as well as parallel lines. Alright, so we're going to begin by considering the special case of this, and that is the m1 or m2 are equal to 0. Not both, just one or the other. So there's a very special case here, namely horizontal lines are perpendicular to vertical lines. This is very easy to see from the picture. So if this is a horizontal line, there's only one line that is going to be perpendicular to it, namely they meet at a 90-degree angle. So as an example, the line given by 3x minus 2 is equal to 5. This line is perpendicular to the line generated by the relation 2y plus 1 is equal to 7. Why? Because this equation represents a vertical line, and this equation right here represents a horizontal line. And that's a special case, and we're not going to really investigate or formally prove that here, so we'll just take that for granted and move on. So for the remainder of this video, we're going to consider the more general case. So we're going to consider two lines here. So line 1, let's assume looks like that. So line 2 is given by the equation y is equal to m2x plus b2. And let's consider another line, say going up, and let's assume that they meet at a right angle. Let's assume line 1 has the equation y is equal to m1x plus b1. Alright, so let's begin a formal proof of the theorem. So we're going to assume that L1 is perpendicular to L2. And what do I mean by perpendicular? I.e. they meet at a 90-degree angle. So our goal is to prove that m1 times m2 is equal to -1. And side note, since the theorem is an if and only if theorem, you should be able to assume that the product is equal to -1 and hence they are perpendicular, but the other direction I leave to the reader or the watcher, whatever you want to call it. So we're going to assume that the lines are perpendicular, that is, they meet at a right angle, and we're going to show that their slopes are negative reciprocals of one another. So we're going to begin by constructing a very simple graph. So consider these two lines. And without loss of generality, we can assume they intersect at exactly this point here. So let's assume that crosses the vertical axis. I'm not really going to call this the x-axis though, because that's going to pretty much let it not be as strong of a proof. So I'm going to call this point A. I'm going to draw another line here. So extend that line out just a tad bit. And I'm going to call this point here and this point here as well. Say A, B, and C. And of course, this is going to be a right triangle as well. I'm also going to consider two angles here. I'm going to consider this angle here alpha, and I'm going to consider this angle here beta. So that means alpha plus beta must be equal to 90 degrees. And I'm going to start naming points as well. So let's call A, let's call that x1, y1. Let's call B x2, y2. Let's call C x3, y3. So this is pretty much all you need in order to set up a decent proof. Now, if you do not know some basic trigonometry from geometry or some identities associated with like tangent or something, then part of this proof may be unfamiliar to you. So I invite you to learn about some trigonometric functions because that's what I'm going to be pretty much basing this proof on. All right, so let's start naming our lines. So this is going to be line 1. Which we already assumed is going to be y is equal to m1x plus b1. And also let's name this line here. Let's call this line 2, which is y is equal to m2x plus b2. So let us find the slope of line 1. So m1, which is going to be the slope of line 1, can be found by finding the slope between point A and point B. So point A and point B is x1, y1, and x2, y2. So its slope is y2 minus y1 over x2 minus x1. So let's just keep that in mind here. We'll need this result in just a moment. Let's also talk about slope 2. So slope 2 is going to be the slope of line 2, so that's the green line. So that's going to be the slope between the points A and C. So that's x1, y1, and x3, y3. So we can rewrite this as y3 minus y1 all over x3 minus x1. So let's box this off because that's going to be important as well. Also, just keep note here that the distance between A and C, namely this can be found by x3 minus x1, or it can be found by x2 minus x1. They are precisely the same exact distance. So we can actually rewrite the second slope as y3 minus y1 over x2 minus x1. So this is the same as m2 as well. And we're going to be focusing on these two equations. So m1 and m2. Okay, great. So now let's look at the tangent function. So I'm going to be focusing first on this triangle here. Right? So what is this triangle equal to? So this horizontal distance is of course x2 minus x1. And the vertical distance is y2 minus y1. That's the height between points A and point B. So we know that tangent of alpha is going to be opposite over adjacent. So according to this picture, that's going to be y2 minus y1 all over x2 minus x1. But we already know that y2 minus y1 over x2 minus x1 is precisely m1. So we have that tangent of alpha is equal to m1. So that's the first important connection here. So now let's focus on the next triangle, which I'm going to highlight in yellow, which is of course a right triangle because that meets at a right angle by design. So the opposite side is going to be this distance here. So that's going to be equal to y1 minus y3, so we're going to do top minus bottom, so this is going to be y1 minus y3. And the horizontal distance is still x2 minus x1, so that's going to be tangent of beta. So tangent of beta, which again is opposite over adjacent, is going to be equal to y1 minus y3 all over x2 minus x1. Now we can factor out a negative sign out of the top part of this fraction and rewrite this instead as negative y3 minus y1 all over x2 minus x1. And of course that is the same as m2, except it's the negative of it. So therefore, we can say that tangent of beta is going to be equal to negative m2. Also, we've already stated that alpha plus beta is equal to 90 degrees. Therefore, tangent of alpha plus beta is going to be equal to the tangent of 90 degrees, which does not exist. Does not exist. Because it creates a dividing by zero issue. So let's keep that in mind. Alright, now let's look at the sum identity for tangent as well. So the tangent of alpha plus beta, in case you're familiar with it, is going to be tangent of alpha plus tangent of beta, all divided by 1 minus tangent alpha tangent beta. So now I'm going to replace tangent alpha with m1. I'm going to replace tangent beta with negative m2. So this is going to be equal to what? So this is going to be equal to m1 minus m2, all divided by 1 minus m1 times negative m2, which is the same thing as m1 minus m2 all over 1 plus m1 m2. So we already said that tangent of alpha plus beta does not exist, so that means this expression does not exist either. So the only way that a quotient of real numbers will be non-existent is if you're dividing by 0. So that means that has to be equal to 0. So that means 1 plus m1 times m2 must be equal to 0, which means that m1 times m2, if we subtract both sides by 1, is going to be equal to negative 1, which is what we sought out to prove. So that means m1 and m2 are negative reciprocals of one another. So if that's the case, that means if L1 is perpendicular to L2, then that means m1 times m2 is equal to negative 1. Similarly, one can show that if m1 times m2 is equal to negative 1, then this will imply that L1 is perpendicular to L2. That is the only possible way that this can be true, is if they are perpendicular. That is, you can't have negative reciprocal slopes and they be like parallel, or they meet at a 30-degree angle or something like that. And I'm not going to prove this. I'll leave that to the interested reader. So combining statement 1 and statement 2, therefore, line 1 is perpendicular to L2 if and only if m1 times m2 is equal to negative 1. And that's the formal proof of the perpendicular line theorem. Of course, if you're not familiar with the trig functions, part of this may not be familiar to you, but I invite you to learn some basic trigonometric identities and some properties of tangent in order to understand this a little bit more. But that's the proof of this theorem, and in the upcoming video, we'll do a couple examples on parallel and perpendicular lines.